Hello. In this video, I want to just briefly revise some ideas on the Taylor series, the exponential function, and differential equations. Possibly things have changed in the years since I sat A-level maths, but I think differential equations are very poorly taught in that course. When I was taught how to solve first-order differential equations, we were basically just taught a method and were given none of the background information on these ideas. This is unfortunate because understanding that background is really helpful when it comes to solving any but the most simple of differential equations. With this in mind, the learning outcomes for this video are as follows. By the end of this video, I want you to be able to write out the Taylor series expansion for a function, and I want you to be able to write out the Taylor series expansion of the exponential function. Now, you've almost certainly learnt this material in the past, but what I hope that you find from this video is that if you understand it this way, these results are rather obvious instead of rather mysterious. Now, again, like I said, you've seen this material before, but we're going to approach the Taylor series in a manner that is perhaps different from the ways you might have seen these ideas in other courses. I think this makes things more intuitive and helps you to understand, but I can understand that some colleagues might feel that this particular approach is very applied and perhaps lacking in some of the rigour of some of the more abstract approaches you might have been shown in the past. Nevertheless, I would like to start by considering the following problem. It takes me 2 hours to travel the 104 miles from Belfast to Dublin. You can thus conclude that I travelled at 52 miles per hour at all points during my journey. Now the reasoning here is obviously fallacious and wrong. I want you to pause the video and to briefly explain to yourself why. The problem is not difficult and you should be able to solve it by considering your experiences of driving in cities and driving on the motorways. Now, hopefully, you have worked out that the reasoning is wrong here because at the beginning of my drive I would be travelling through Belfast, where the roads are narrow and the speed limits are 30 miles an hour. Once you have escaped the hustle and bustle in Belfast, you are out on the motorways, driving at considerably faster speeds. Lastly, when you reach Dublin, you are back in the traffic at the centre of a city, which slows you down again. What I would like you to do now is to imagine you split your journey up into 10 time windows of 12 minutes each. Draw a line representing the total distance between Belfast and Dublin and mark on this where you are after 12 minutes, 24 minutes, 36 minutes and so on. Pause the video now and take a moment to do this. Hopefully you have drawn a diagram something like this. In early time windows you don't move very far because of the traffic in Belfast and because you are travelling slowly. In later time windows when you are on the motorway you travel considerably further because you are travelling faster. However, at the end of your journey you slow down again and once again you travel only small distances in these equal time windows. Now let's introduce some algebraic symbols to describe this process. We will call the 12-minute time window delta t. The distance we moved in that time by contrast we will call delta x. We now ask the question, can we write delta x in terms of delta t? The answer to this is an unequivocal yes. We can write delta x in terms of delta t using the following power series. It perhaps looks like I just pulled this formula out of thin air, and to be fair I did, but there was a good reason for it. We use these sorts of power series to represent real numbers all the time. In fact, you personally use power series to represent real numbers all the time. If you are not convinced, try setting delta t equal to 0.1. 0.1 to the power 1 is 0.1, so the first term in our series is a number multiplied by 0.1. 0.1 squared is 0.01, so we add this to our first term, we add to this first term a number multiplied by 0.01. 1 cubed is 0.001. So we now have a number multiplied by 0.1 added to a number multiplied by 0.01 added to a number multiplied by 0.001. Now I could proceed with this process forever, but hopefully you are getting my point, which is that decimals that we use to represent real numbers every day are just a particularly compact representation of a power series like this one here, with delta t set equal to 0.1. I want to make one further small change before I move on with this derivation. I want to rewrite the delta x part as x of t plus delta t minus x of t, as shown here. These two numbers, x of t plus delta t and x of t, represent my position at time t during my journey and my position at a time delta t later, as shown on the figure. With this done, let's turn to the problem of determining the various coefficients, the ANs, in this power series. Our first step in doing this will be to divide both sides by a factor of delta t. This gives us the following. Next, we are going to take the limit of both sides of the equation as delta t tends to 0. For some of you, the left-hand side may now be equal to something familiar. If it is not familiar, don't worry about it, we'll come to that in a minute. Let's look now at the right-hand side though. The first term in our series has n equal 1, and thus a to the 1 multiplied by delta t to the power 0. Now, as we all know, if we take any number and raise it to the power 0, we get 1. The first term in our series is thus a1. In all subsequent terms, we have an multiplied by delta t raised to some integer power that is greater than 0. However, we are taking the limit as delta t tends to 0, and thus these higher terms will all tend to 0. Consequently, the sum on the right-hand side reduces to simply a1. We thus find that the coefficient of the first term in our series on the right-hand side, a1, is equal to this limit. The limit is x of t plus delta t minus x of t all over delta t. The limit is at delta t tends to 0 of x of t plus delta t minus x of t all over delta t. On top of this, this limit is the definition of the derivative, the first derivative of x of t. The first coefficient in our power series expansion is thus equal to the first derivative of our function x of t. Before we continue, let's just briefly take a moment to convince ourselves that the limit shown here is equal to the derivative. In doing this, let's consider a nice and simple function, x of t is equal to t squared. Now we all know that the derivative of this function, dx of t by dt, is equal to 2t, as this was probably the first thing you ever learnt in calculus. We are now going to differentiate t squared using what we call first principles by solving the limits shown at the top of this slide. We begin by substituting our function x of t equals t squared into x of t plus delta t and x of t as shown here. Next, we multiply out the bracket containing the t plus delta t. Cancelling factors of plus t squared and minus t squared, and the factors of delta t on the top and bottom of this expression, we now find that we must take the limit as delta t tends to 0 of 2t plus delta t. Obviously that this is equal to 2t QED. Let's now come back to this business of writing a change in a function, f of x plus delta x minus f of x, as a series expansion. We've already shown that the coefficient of the first term in the power series is equal to the first derivative. We might therefore be tempted to assume that the coefficient of the second term is the second derivative, the coefficient of the third term is the third derivative, and so on as shown here. We would be totally wrong in assuming this, however, and it is easy to show why. Imagine if f of x was equal to x squared. We know that the first derivative of this function is 2x, that the second derivative of this function is 2, and that all higher derivatives are 0. The series expansion on the right-hand side of our wrong equation is thus simply 2x delta x plus 2 delta x all squared. If we look at the left-hand side, however, we have delta x plus delta x all squared minus x squared, which, when we multiply out the brackets and cancel terms, is equal to 2x delta x plus delta x all squared. The equality in our bogus equation thus does not hold because the coefficients of delta x on the right and left-hand sides of our equation are not the same. It turns out that it is easy to fix our blunder, however. We simply have to multiply each of the terms in our expansion by a factor of 1 over n factorial as shown here. This gives us the Taylor series that should be reasonably familiar to you. Let's now convince ourselves that this equality is true by considering the function f of x equals x cubed. The first derivative of this is 3x squared, the second derivative 6x, the third derivative 6, and all higher derivatives are 0. When we substitute all this into the power series on the right-hand side of the equation, we thus get the equation shown here. Furthermore, when we remember that 1 factorial is 1, that 2 factorial is 2, and that 3 factorial is 6, this then reduces to the equation shown here. If we consider the left-hand side of our Taylor series functions our Taylor series function, this is x plus delta x all cubed minus x cubed. It is easy to show that this is equal to the formula that we just arrived at for the power series by multiplying out the bracket and cancelling terms. At this stage, all this business of the Taylor series perhaps feels a little circular and pointless. Why would we calculate x plus delta x cubed minus x cubed using a Taylor series? We could just calculate this directly after all. The Taylor series is important, though, because once we have introduced this more abstract representation for differences in functions that we can represent using power series, we can begin to play. For example, let's imagine that we introduced a function g and required that at all points x, at all points along x, the derivatives of g of x were equal to the value of the function g of x. In fact, let's make this even simpler and insist that g of x and all its derivatives are equal to 1. Substituting these values into our Taylor series and expansion and rearranging, we thus find that g of x plus delta x is equal to the following. Incidentally, notice as an aside, we could have set g of x equal to anything and taken this factor out of the sum. Thus, if we had g of x equal to a, the right-hand side of this expression would become a plus a multiplied by the summation shown in the second term here. Okay, so this sum perhaps does not look particularly exciting. Look what happens when I differentiate with respect to delta x, however. For each of the terms of 1 over n factorial multiplied by delta x to the power n, For each of the terms of 1 over n factorial multiplied by delta x to the power n, we lower the exponent by 1, giving delta x to the power n minus 1, and multiply by n, giving 1 over n minus 1 factorial, as shown here. We can then simplify the resulting expression to give 1 plus the sum over all n of 1 over n factorial multiplied by delta x to the power n. But hold on, this is just the original power series we had for g of x plus delta x. In other words, for this particular power series expansion, we have found that the derivative of g of x plus delta x with respect to delta x is just g of x plus delta x. Now normally we might write this differential equation slightly differently. We often set x equal to 0 and then get rid of the delta x. I think this is fine, but that we should perhaps, when we first show this to students, differentiate with respect to delta x rather than x, so as to make clear to them that when we write a differential equation, the dx represents an infinitesimal change in the argument of the function, a change that at least has a direction, if no magnitude. Let's now get back on topic and consider the result we have just arrived at. Just why is this differential equation so exciting? Well, it comes up everywhere. Consider, for example, population growth. The rate at which a population grows will be controlled by the number of females who are capable of reproducing. In other words, the rate of change of the population size, dg of x by dx, will be equal to some scalar quantity lambda, the fraction of the population which are females of reproductive age, multiplied by the size of the population g of x. Consider instead the amount of, which is precisely the equation we have here. Consider instead the amount of money in your savings account. If you do not spend any of it and just leave it in the account, the bank takes the amount you have in your account and increases it by multiplying what you have by some constant factor, the interest rate. You thus have the rate of change of the amount of money in your account, dg by dx, is equal to the interest rate, lambda, multiplied by the amount of money you currently have, g of x. These are just two examples of where this differential equation comes up, but there are many, many more. What is more, you should know many of these examples, and you will almost certainly, at some point in your mathematical career, have been shown that the solution to this integral is g of x equals a e to the lambda x. What we have added in this video is an explanation of precisely what e of x is equal to and where this quantity comes from. E of x is given by this infinite series, and this comes about because this is the only power series which is equal to all its own derivatives. Pretty cool. So one last thing before I finish, because it really pisses me off when I see it done wrong in exam scripts. Notice that when I solved dg of x by dx, I wrote that g of x is equal to a e to the lambda x. Now the thing that irritates me is when students simply write that the solution of dg of x by dx is equal to e to the lambda x directly. I cannot emphasize this enough. This may be correct, but only because you have been given the boundary condition g of 0 equals 1. In my view, not mentioning this boundary condition is just wrong and inexcusable. It is hugely important, not least because if you are told that g of 0 equals 0.5, and you ignore this and just assume that g of 0 equals 1, your final equation will be just wrong. With that rant over though, I hope you have taken something away from this video and that you now understand the Taylor series and the exponential function a little bit better. Thank you for your attention.